Dear colleagues, allow me to open the meeting jury for the defense Viktor Duplyakov dissertation, machine learning on-field data for hydraulic fracture generalization. I will start by brief introduction of the members of the jury. Professor Clement Fortin is and professor of Schooltech, Dr. Fortin has joined Schooltech in April 2014. Between 2014, Professor Fortin was the president and CEO of the consortium of the research innovation in aerospace in Quebec. He has been the director of the Department of Mechanical Engineering at the College of Polytechnic de Montreal and professor in this institution since 1987. Dr. Fortin created Polyclone Technology Incorporation, a spin-off company of NIC. The company developed an innovation PLM solution for engineering. Professor Fortin is a fellow of the Canadian Academy of Jury member Professor Alexander Shapeyev, graduated from Novosibirsk State University in 21 with a bachelor degree in 23 with a master degree. He earned his PhD from National University of Singapore in 2029, focusing on the topic of computational fluid dynamics. During the two postdoctoral at EPFL Lausanne, Switzerland, and the University of Minnesota in the United States. Professor Shapeyev concentrated on the mathematical analysis of the coupling of atomistic and continuum description of solids. His work was with 2013 SIAM outstanding paper. His primary research interests lie in the development and practical application of model interaction, often referred to as interatomic potentials. His work finds application in the field of material science, physics, and chemistry. Two members of the jury are present and online. Dr. Dmitry Karagash is a professor of civilian research engineering Dalhousie University of Halifax. He received his bachelor and master student in applied mathematical mechanics of Moscow State University and PhD in geological engineering from University of Minnesota. His research interests are in solid fluid mechanics, geophysics, resource engineering, earthquakes, and hydraulic fracturing. He applies principles of theoretical mechanics and physics to problems for earth sciences, resources, and geotechnical and environmental. He has published more than 100 peer-reviewed papers and has an H index 26. And jury member Igor Dontsov joined prior to joining REST. Igor worked as one content laboratory at the University of Houston as assistant professor and the University of British Columbia as postdoctoral research and teaching fellow in the mathematical department. He earned his PhD degree in engineering at the University of Minnesota and bachelor degree with honors in physics at Novosibirsk State University. Igor primary area lie in the theoretical numerical modeling of hydraulic fracturing, propellant transport, and geomechanics. He has been exposed to the development of several academic and commercial simulators of hydraulic fracturing, propellant transport, and flow. Igor served as a reviewer for dozens of journals and several scientific proposals within and of the United States. Igor has published over 50 peer-reviewed papers and received several awards, including our outstanding auditor service awards. And now I would like I would like to present the supervisor and cost of our candidate. Supervisor is Professor Andrei Osiptsov. He is the director of and professor Project Center for Energy Transition. ESG, Scientific interests of Professor Osiptsov lie in the field of asymptotic method, multi-phase flow modeling, suspension flows, and new technology for oil and gas industry, in particular hydraulic fracturing. He has 50 publications, including 30 papers, indexed and scopus, and over 6 granted patents. Professor Osiptsov is a member of Society of Petroleum Engineering, reviewer for a number of professional journals. As co-tech, Andrei Osiptsov is involved in research projects in collaboration with Russian companies and academic institute on them related to technology of energy transition. And supervisor candidate is Professor Evgeny Bornaev. He is absent. He is absent. Yes. Evgeny Bornaev from Moscow Institute of Physics and Technology in 26. After getting a candidate of science degree from the Institute of Information Transmission Problem in 8, he stayed with the institute as a head of the data analysis and predictive modeling club. Since 26, Evgeny Bornaev is an associate professor in School Tech, CDICE, and a head of advanced data analytics in science and engineering group. Since 2022, Evgeny Bornaev is a full professor and the director of School Tech Applied AI Center. In 2022, degree of Doctor of Physical and Mathematical Sciences in Moscow Institute of Physics and Technology. Evgeny's current research focuses on the development of new algorithms in machine learning and artificial intelligence, such as deep network for approximation of physical model, generative modeling, and manifold learning, application of computer vision and 3D reconstruction, near visualization. The results are published in the Computer Science Conference ICML, ICLR, NeroIPS, NIPS, CVPR, ICCV, and ECCV. And now let me to introduce our candidate, Viktor Duplyakov. He got his bachelor degree and master student degree in the field chemistry in Gubkin State University of Oil and Gas. Worked as a junior engineering at Gazprom Neft, where the critical well rate estimation model to reduce the risk of water conning in oil wells, automated selection of the wells for pump rate increase. Worked as engineering in the soft. Thank you for attention, and if there are some questions to me, no? So let me, now I give the floor to the candidate. Viktor, please try to keep it to 40 minutes.
Okay, thank you. Thank you, dear Chairman, dear members of the jury. Yes, and
can you later move this one, minimize it to this one? Yeah, because it's taking part of the slide. Good.
there would be possibly a number of slides will be there.
Yeah, the slide numbers are important because it's best to know. Thank you.
Good afternoon, everyone, dear members of the jury. Thank you for joining me on this day, and I would like to present my thesis named Machine Knowledge data for hydraulic fracturing design optimization. The thesis made is under the supervision of Professor Andrei Sipsov. Co-supervisor is Professor Evgeny Burnaev. So I will start with a brief description of what hydraulic fracturing actually is. My pointer doesn't work. Okay. So a brief description of the hydraulic fracturing. Is it? Hydraulic fracturing is a process of creating fractures in a reservoir for oil and gas production intensification. Do it by injecting fluid, often is high viscous fluid, to create fractures. It's PET. And after the PET, we inject fluid with some propant. Propant is a small ceramic or sand particles, a few millimeters wide, that prevent a fracture from closing again. And if we are doing it multiple, for example, in horizontal wells, we move to the next section and repeat it one more time. So the created fractures are usually up to several of meters long, several meters high, and several millimeters wide. Therefore, these fractures have very good permeability and they enhance the production from the oil or gas wells. So importance of the hydraulic fracturing cannot be overestimated. After the so-called shale revolution in the United States and throughout the world, the number of the percentage of unconventional, so-called conventional or low permeable reservoirs rises. Therefore, the amount of conducted hydraulic fracturing treatments also increases, as hydraulic fracturing is the most successful way to extract oil from such reservoirs. So the effectiveness of treatments becomes more and more important. Therefore, there is huge profit potential in optimizing fracturing design. My goal, the goal of this work is to optimize hydraulic fracturing design to maximize oil production from a well. We need to digitize the expertise of hydraulic fracturing engineers to construct a pipeline for fracturing design optimization and develop a type of a recommendation system for fracturing design optimization based on gathered field data. And to do this, we need to construct a field data. Based on this database, we can create a model for predicting cumulative fluid or oil production by known parameters of the well, layer, fluid properties, and fracturing design parameters. Then we obtain parameter limits further optimization, and at the end we can optimize design using the model created on the second step. The first and the most crucial part in this work is data gathering, one of the most crucial parts. Itself is crucial for creating valid machine learning models. And data gathering takes on average 74% of the entire time in every project. And while gathering the data, an engineer encounters a lot of problems. The data is low quality, it has high uncertainty and accuracy, especially in our case within the field of production. And data often comes from multiple sources. There are and missing values. We need to somehow deal with it. Data in our case in this study comes from the 22 fields located in Western Siberia from the 2013 to 2020. Number of wells is about 5,500. It includes vertical and directional wells as well as horizontal ones. Number of operations exceeds 6,600. It includes as single stage as well as multi-stage treatments. And this data comes from different sources, diverse one. It coming from lists from the operating practices, PVT properties of the fluid, monthly productional reports, well logs interpretation, geomechanics, and layer intersection data. And overall number of parameters is 296. And after the analysis, after feature elimination, we decreased the number of input parameters till 30, including 21 parameter describing the formation reservoir, 11 parameters about well, and 6 parameters on fracturing design. And 1 parameter is output, our target, considering production. So to conclude, here is a comparison made by colleagues from China. I think they compared several studies with the same objective of predicting production. As you can see, the number here is a column with the number of rows in a database, and our database is the most complete, biggest throughout the competitors, I would say. To successfully optimize the Gödel fracturing design, we divided our tasks into 2 subtasks. We call it forward problem, which is the prediction of oil production on a fractured well, and the inverse problem, optimizing the production using the from a forward problem. So about the forward problem, there are 3 general of methods for predicting production. They called analytical, numerical, and data-driven methods. So for the analytical, for example, we have, they are quite simple, relatively simple. They require fewer data inputs, and they are suitable for quick estimates production, but they have limited applicability for complex reservoirs and conventional ones, for example. And for the numerical methods, they can model complex geometries. They account for multi-phase flow and fluid interactions. They are suitable for long-term production forecasting, but the main flaw is they require extensive data and high computational resources. They can calculate for days or weeks even. And for they require complex calibration processes such as history matching. And data-driven methods kind of fill in a niche between those previous 2 groups. They may capture complex patterns. They can adapt to reservoir conditions according to changes in data. They are useful for data fusion from various sources, but they require substantial amount of labeled data for training. They require a good quality of such data, and interpretability and may be challenging, especially in the case of the neural networks. So for the methodology of the forward problem, we need to predict our target, our production data from the input vector of 37 parameters, to somehow train our model to predict the production. And in our study, we used the 5-fold cross-validation technique. Briefly describe it. So firstly, we split the all data into the training and test sets, and we don't touch until the final evaluation step. It remains hidden till for the time of the training. And then we have training data and we divide it by 5. So for each of the 5 steps, we train model on the 4 folds and validate on the fifth one. In the second step, we change the validation fold and repeat it 5 times. In this case, we can find parameters for model tuning and get the optimal models parameters. And after that, after the gap parameters were found, we train a model on all of the training data and do step on the whole out set or test data set. It's called. As a target variable, we have chosen a logarithm of cumulative fluid production for 3 months after the treatment. And for such kind of target, the most successful algorithms in terms of predicting capability was CatBoost. Algorithm from the family of decision tree based algorithms. But for the final model, we used a more complex approach with rich regression and a CatBoost. So firstly, we did an initial guess on strong features such as net pay, overall pay, overall height of the reservoir. It was a propant mass and propant concentration. We did initial guess on these parameters via rich regression. Rich regression is a kind of linear regression with L2 regularization. Then we subtracted this rich regression from the actual true target value and attempted to predict this difference via CatBoost. And after summarizing the predictions, we get output. So if we compare the metrics for the CatBoost and stacked models, we can see that CatBoost slightly outperforms the stacked approach by 2% in R-squared metric. So, but why? Why did we needed such a complex stacked approach when we get lower metric? It's basically worse. So to answer this, let's see the next slide. Here is instances of a target. Y-axis is the target, and x-axis is the parameter for the design parameters. So we have, for example, let's look on the propant mass section. Here we can see that for the CatBoost, for the stacked approach, for example, we have a smooth increasing and basically it's what we expected from the model, because in our case, in our field, there wasn't any water-bearing formations. We just had only oil, and we expected from the model to know that if we pump more propant, we get more oil or fluid in the reservoir. And as we can see for the stack for CatBoost with green line, we have some peaks, and it's very basically it's unexplainable. So stacked approach here, despite its slight decrease in prediction capacity, indeed creates smoother dependencies. For the next task, we basically can do we can divide our database into 2 parts. Refracturing treatments and treatments garlic fracturing on new wells. So here with new wells, it's like we just drilled a well, we perform fracturing on it. And for the refracturing treatments, and when we already have operating well, we know the production from it, and we fracture it again to boost the production. So how these plots. It's called the Shapley plot. For each of the parameter, we have points of data, and each point represents every row in the database. So, for example, here for the fluid production before hydraulic fracturing in the refracturing treatments, we have a red point which corresponds to the high value of the fluid production before the fracturing. And the position of the point respectively from the zero line tells us where this high red high of the feature drives the model output. So, for example, high fluid production before the fracturing corresponds to high target value, which means the more we get from the well before the fracturing, the more we will get after. That's what the model tells us. And as we can see, for the new wells, we don't have such parameter as a fluid production before the fracturing, because we didn't. So it's harder to predict production on new wells. But that was what we were doing during this study. As a result, we can point out that the family of decision tree-based algorithms show better accuracy than other approaches. The CAT boost algorithm based on the gradient boosting decision trees outperforms all other methods. But for obtaining meaningful predictions, more complicated that includes linear regression was required. And for the inverse problem, we have an optimization of fracturing design. As was mentioned, it was mentioned before, the input vector of input parameters contain well construction, data formation parameters, PVT properties of the fluid, and fracture design parameters, which are stages in multi-stage hydraulic fracturing, proppant mass pumped, final and average proppant concentrations, pad share, and the pumping fluid rate. And we need somehow to determine what optimal values for each of the fracture and design parameter. So we need to figure out what would be the lower and upper boundaries for the optimizations. And with this, we come to similar algorithm, which allows us to screen throughout the whole database. We can screen the of wells for similarity to a pilot well. So, for example, here is a window from the application developed as a result. Here we can fill in the parameters of the pilot well. We can point out the layer, for example, the phase, it's new or refracturing treatment, or we can look for the wells within a vicinity, some distance, some radius well. And for each of the subset of this well, of such wells, we will calculate a similarity. So a similarity metric can be either Euclidean distance or cosine similarity. So as a result, we can analyze previously conducted treatments on similar wells fast, simply, and straightforward. We can import parameters, for example, of pilot wells with average values of similar wells, and find basically the boundaries, limits for further optimization. And for the such boundaries, we choose to have fifth and percentiles within similar wells to exclude outliers. After that, for each of the design parameter, we get such limits via similar well search. And after that, we have two options. We can go for making a grid for all combinations of all parameter values within the certain step, make a Cartesian product of all the combinations, and predict the cumulative fluid production for each of this set. Or we can use an optimization. And to compare two approaches, for example, within the grid search, it's fairly easy to implement. In this method, we have a uniformly covered hyperspace, but as a flow, as a cons, we can likely get only near optimal solutions. For the optimizational algorithms, for example, differential evolution, we tried also squares programming, particle optimization, and surrogate-based optimization utilized the concept of probability. Here we more likely will get global optimum. We will get randomly covered hyperspace of the parameters, but they are dependent, which means successfulness of finding the global optimal will be dependent of the hyperparameter values for these optimization algorithms. And also an point to note, the target selection, because target tested in this work was the cumulative fluid production. And the reason for choosing this target was to figure out if it's possible to successfully construct a model that can capture key dependencies of the hydraulic fracturing process and find out if it's possible or not. In this case, optimization, of course, tends to favor larger and more numerous fracturing operations. It tends to increase constantly the propant mass, for example, or number of fractures. So the production should include economics targets, such as net present value, investments, how it's done in fractate and kinetics from Schlumberger, and either or we can use some joint metric, for example, on PV per section with discounted returns of investment, how it's done in REST software. As a conclusion, with the use of the optimization algorithms, we can find more optimal solution, but grid search is useful for one variable at a time analysis, which I will show a bit later. Similar well search can be used for obtaining design parameters optimization limits, and such limits from 5th to 95th percentile are useful for eliminating outliers, therefore for improving the consistency and accuracy of models prediction. As for results, we conducted a field test that was carried out on 21 and this amount of wells included 9 horizontal and 12 vertical ones, and 7 of these 12 vertical was multi-pay, which means that they are operating on several layers simultaneously. And the accuracy of the prediction model field tests was close to the holdout set accuracy check. It was about 30% in weighted percentage error. And important to note that the distribution of well types, vertical, horizontal, and multilateral, for field tests was that presented in the holdout set we checked the model upon. When we algorithms for optimization for the inverse problem, here we can see a plot dependencies of fluid production, how each of these algorithms optimize the target value up to which level. So the higher the better. And while optimizing wells from 10th to 21st well, all algorithms perform quite similar. But with horizontal ones, The most successful algorithm was surrogate-based optimization, followed by least squares programming and evolution. Then we compared what could be done, what output, how much more production we could get from each well if the design was so all optimization was done with a constant propant mass, and red bars represents predicted production from the real with the real design, and the blue bar represent the optimized production with the use of the optimization. We can see that hypothetical average production increase was 38% on average. And as a side result, or even a main result, the useful application was developed for petroleum engineering. For example, for the first window, we can see here we fill in the parameters for the pilot well. We point out the field and the layer of a well. After that, on the second window, we can obtain the parameters within which they will be optimized. We choose a step of the grid search optimization technique, and after performing such optimization, we can see the dependencies plots, one variable at a time analysis. These plots show how a target would change if one would be varied from the low to the lower to upper optimization boundary. It allows us to calculate over 1.5 million designs per minute, so it calculates very fast. And final step, we have a pumping schedule which shows which propant concentration should be on the wellhead while pumping, performing the treatment. So as for the future work, it would be useful the applicability of the approach by introducing, for example, new features, distance to upper and lower water-bearing layers, because in our case, there was no aquifers in the oil field test, and construct models, for example, for predicting water cut, not only production but water cut also. And for the accuracy, we can combine synthetic data from fracture design simulations, from the numerical simulations of the production predictions, and account for the influence of injection wells. And to implement such a feature to optimize based on the economics. So choose a different optimizations, NPV or returns of investments. It would be quite helpful, and it's not so difficult to do if we have a predicts production. So as a general conclusions, we can say that developed data-driven model is faster than numerical, but have also a pretty good accuracy. The database constructed so far the biggest compared to those from the literature, and on-the-fly optimization pipeline limits allows to screen for all of the find the optimal set of design parameter value within a few seconds or minutes long. So I thank you for hearing. And as for publications, work was published in 2 papers, one submitted, presented on 2 conferences, and our team defended patent, submitted and defended it successfully. So thank you for listening. If you have any questions, please.
Thank you, Viktor. Did you introduce some changes to the review after the review, to the taste after the review?
Yes.
Could you say which exactly changes?
It was changes in I corrected typos. I did restructured a bit the fourth chapter. I corrected the figure captions and added some bullets in the conclusions.
Thank you very much. Colleagues, question please. Please, if possible, confirm also whether you are satisfied or not with the changes introduced to the review. Professor Fotin, your question?
Thank you very much. Let's go to slide 9. Thank you for the presentation. And on slide 9, where you compare to other fields, of course, you have a phenomenal size of data, and this is really great. But on the accuracy, what do they call the accuracy there? Because you're on the low side. I see 97% is phenomenal. How do you see this?
Yeah, so thank you for the questions. I checked this paper, of course, we checked it, and the accuracy here is 97% R squared, and they were forecasting gas production. So it's quite different in terms of accuracy, I suppose, because that's my proposition, because I don't know if it's would be the same if we were optimizing predicting the gas production.
But is it this accuracy, is it on the same parameter, or it's, like you say, is it always on the production volume?
They did, in this particular paper, the accuracy was on yearly production or cumulative gas production for the year after the treatment.
Okay, thank you. The differences between CAD boost and the stack approach is kind of surprising to me, because when you compare them statistically, they're comparable, or where when you show the graphs, they're very, very different.
Yes, it was surprisingly for us also, because when we noted the difference and unexplainable behavior of the CAD boost algorithm, it became clear not suitable for our approach in design optimization.
But then why it didn't show it in the statistics is my question, because if you such a behavior, it's very, very different. Why it would not have shown up on the basic statistics like this? 14.
These statistics, the CAD boost may have been overfitted. So it actually the points, observation points in database, but it will not successfully extrapolate on the unknown data.
Okay. Now, maybe what do you see as your most important contribution in your PhD thesis to the field?
Yeah, I can say it would be the similar algorithm, the pipeline itself for the finding the most similar wells. It from the actual petroleum engineers that it's really useful for an engineer to fast and very easy and in understandable way to see which treatments maybe were very similar to the one they're going to do.
And what do we see as future work, and what do you think is the most promising next step for your work?
So most promising steps would be maybe it would be introducing an economics target, because it's quite simple after in all these algorithms and models. It would be most logical step, I think, after that, to optimize not at production, only the production. So I think that would be the
next step.
Okay, sorry. And one last question, probably obvious for people in the field. Why are the horizontal wells much more productive than the vertical?
So with the horizontal wells, it would be horizontal wells when we have several fractures. Of course, we can cover more volume of the connected to those fractures in some way. So it would be much more productive to horizontal one. Of course, it's much more expensive to build. It requires a lot of knowledge and tools to build it, but it's more productive.
Okay, thank you very much.
Thank you.
Thank you. Are you satisfied by that? Professor Shapey, a question from you.
Yeah, thanks. I have first let me read out the questions that are, then I had two more questions. One was already asked by Professor Fortin. So I think when I read your thesis, you were writing something about the bias and the data. I don't remember exactly what you wrote. You didn't feature in the presentation. So is there bias in the data, and what are the potential sources of the bias?
Mm-hmm. I would say the most biased data, the most biased would be induced by a human. It would be biased. For example, if you looking on the frag lists where we have a description of all the stages for fracturing, we can see a lot of typos, a lot of misunderstanding of the what each cell in Excel sheet is required to fill in. So it would be like that. As for the underground reservoir, we don't know much between what is happening between the wells. Another sort of uncertainty is the that we don't know what is between the wells. Another source of uncertainty would be inaccuracy of the sensors we used for example, for well logging. So that would be, I think, the uncertain thing in data.
Okay, thanks. So my second question, so can you comment about the 64% accuracy? So there was already a question about comparing to other data. Mm-hmm. So my understanding is just different data. You cannot compare directly. But let's say 60, when you have 65%, right? Is it a lot or a little? Can you improve? It's also related to the question of what's the most promising next steps, right? So it looks like you are satisfied with this accuracy, and steps would be to count money, to optimize, I remember, some numerical performance. So the accuracy, do you think it can be improved, or is it that's already good enough and you should move on to applications?
Mm-hmm. So for the accuracy, of course, it should be improved for using it without, for example, numerical simulators. So the main goal for our application would be to for the similar wells to do some quick analysis, some feature dependencies. It will be quick, and then we can, for example, for the numerical simulator, we can restrict some things we are going to so as for the accuracy, the next steps would be to introduce an inference for the from the injection wells. We think it would be it's very promising, and to fill the data even more, to increase the number of points in database. That should be.
Mm-hmm. Yeah, thanks. I need to ask my third question that I wrote here, although you pretty much answered in the presentation. So the potential challenges for implementing a recommendation system in a real world scenario, you showed already let's say, interface of an app. Do so understand it's like a lot of things are ready, but so how do you see the perspectives? Like, how far is it from product that can be used by the companies?
Actually, it's already implemented. A few tests were conducted by an actual engineers. They found it quite promising in terms of screening for the quick screening for the fracturing parameters and weld properties. And for the problems, for example, we need to train a model for each oil field separately, and not for each oil field it would be as accurate as for our case. So the main problem would be continuously conducting research on different oil fields
But just to understand, just to make sure I understand it correctly, when I say train, you mean to inject the data particular oil well that is being optimized into the model? Or what does it mean? Because you have data.
It means that we have data on different oil fields, and for example, we trained a model, tried to predict it for different oil fields. For example, here is accuracy for one of the oil fields we tested, and for the different oil field, it wouldn't be such accuracy. It was lower, in fact.
And how would you retrain? You would take different data?
Yes, I will just take other oil field. Okay. So, for example, in our case, it's all 22 oil fields, and for the one oil field, predominant oil was about a little bit more than half of the data.
Okay, so my last question, presented this comparison. There's a grid search approach and there's a Bayesian approach. And so which one did you implement then?
Both, basically. So for the grid search, for example, it's very useful for an engineer to see this at the time analysis. So the engineer, an engineer can tweak these parameters right or left, lower and upper boundaries for the optimization, and see how the dependency changes. So for example, we want to see what happened if we increase the propellant loading.
Yeah, so I think I understand this. My question is, if you have 1.5 million designs per minute, do you really need an approach?
It seemed that yes, because 1.5 million not enough to cover all of the hyperspace if we increase the number of steps in the optimization. So we have number of steps power to number of parameters we are going to optimize.
How many parameters do you have?
6.
Okay, if you increase much beyond 10, okay, got it. Okay.
So we can, yes, we can aim into the between the point we can
okay,
lost.
Yeah, Thanks. No more questions. I'm satisfied. Will I get a chance to speak later or not? Will I?
Thank you.
Are you satisfied with those answers? Yes, yeah. And now the question from colleagues present online. Professor Garagash, do you have any question?
Right. Could you hear me? Hello? Could you hear me?
Yeah, we can't hear.
You can't hear?
There are two messages in the chat.
Maybe Dr. Dantsov?
Hello. Can you hear me?
Igor, I can hear you, but
I heard you too, but it looks like we are.
Yeah, okay. We're trying to get our. Can someone say something online?
Hello.
hello.
Can you
Okay,
hear
we
us?
can hear you. Elena, can you
Can
make
you
it a little louder?
can you
Yeah,
hear?
almost. Yeah, we'll just make it louder and then we'll be ready to take questions. Can you say something?
Right. Here is Dmitry. Yeah.
Okay, thanks.
Please, Professor Garagash, do you have a question?
Yes. Yeah. I certainly do. Well, just to say, to start, I appreciated reading the thesis quite a bit. I mean, I think it's well, as a bit of an outsider in the machine learning team, I think it is a very important direction to take, given that the wealth of the data on the treatments. And so, yes, it was quite an interesting personal experience to read the thesis and the results of the study. And yes, I do have a few questions. So I guess, again, another general comment maybe to Viktor in addressing the written questions in our reviews that we posted to you. I mean, it probably would be useful to to have more specific pointers of where in the text you made the changes. For example, highlighting the revisions within the text, just like you would do for a paper revision for a journal, and maybe writing a little bit more in that log of changes, how you have summary of how you address those questions would be also helpful, like a rebuttal letter for a journal. Just a comment. I think that would have been useful. Right. So now to the specific questions. If you could come back to that slide 9. So a few colleagues commented on it already, where you compare the different studies. Slide 9. So I'm also a little puzzled by this, this amazing, the studies with the amazing accuracy numbers, etc. And I think I have a feeling, what I recall from reading the thesis, that you have commented on why, in some of those studies, the accuracy was such a superior number, because perhaps it was a smaller data set or more homogeneous data set. But could you perhaps reiterate on that? What do you attribute, if you have an idea? So what do you attribute such a great performance of some of these other models? And as you do so, I mean, were there some other features or data features that were included in the studies, like you were mentioning, that perhaps included in the injection well data into your analysis would have made improvements so as a future work? So was there what were the differences, I guess, that led to this accuracy figures, to different accuracy figures?
Okay, thank you for the question. And as for the accuracy from the first paper, it was a prediction of, it was a cumulative guess prediction from the Marcellus shell. So it's a little bit different objective, and I think that we cannot compare our directly in terms of accuracy of our models, but the accuracy is indeed very very amazing. So some other papers where we can see the papers, 3 papers with 79, 72 and 85% of accuracy. It was conducted on a database with hundreds of points. So it's very hard to determine if the accuracy presented can also be comparable to our holdout set of more than 1,000 wells. So they have been resulted in overfitting of some algorithms they were using. As we can see, they were using neural networks, for example, that tends to overfit. So it can be attributed to this. And as for the improving of the accuracy of our models, so introducing some parameters, for example, again in the first paper, the one parameter, the one feature we didn't have was data from the bottom hole pressure sensors. They had it, I think, month by month, and we our data of such type was not accurate at all. And yes, for improving the accuracy, we can introduce new features such as I don't know, again for the injection from the neighboring injection wells, volume of production from the neighboring production wells, etc. We can use neighboring neighborhood, some kind of neighborhood properties to boost the accuracy of our models. I think, yeah, that's it.
Yeah, thanks for the answer. I guess I have perhaps, you know, still on that same topic. Are any of those data sets, other data sets in these other studies available? Have you tried, for instance, applied your workflow and your ML model to any of these data sets to compare the performance?
There were studies on backend shell with open source data, but I think we didn't try to implement our models on this data. So it would be it can be done, yeah.
I think that would be interesting to basically to compare the performance. And just a clarification question on the what you said with regard to this first study with superior accuracy. You said something to the extent that is a gas, it's a gas production, and therefore it's very different, and therefore it's not comparable to basic. Could you elaborate on that a little bit? I didn't quite understand why is this apple and oranges and they're not comparable, these two studies, or what's the exact reason for this difference, and why they are not comparable, why they can be compared?
For my knowledge, it will be difficult to compare. For example, if we are having fluid interactions, fluid between, for example, oil-water interactions in multi-phase flow, it's harder to model interactions comparing to the just gas. So I think it would be attributed to this. It can be.
I see. So in your case, these were the fields, I guess, multi-fluid fields. That's what you mean? That may have had a more complicated multi-phase physics involved. That's what you meant by that?
Yes. So in our case, it was mostly oil field with induced water from the.
Sorry, the last part of your answer was eaten by Zoom. I couldn't hear it.
Yes, oil field with primarily oil with induced water from the injection.
Is that's your case?
Yes, yes.
Okay. Thanks. Well, and maybe the last small question on that same topic. You mentioned in the thesis that perhaps, and I think you have demonstrated it graphically as well, comparing, the accuracy of the forward ML modeling of yours for different wells, even within this large study, right? And there was a comment and quantification of it that horizontal wells, right? So what are we looking at? Yeah, field test. Prediction, right? So that's the error plots, right?
Mm-hmm.
Yeah. So basically, the vertical wells through multilaterals performing the worst, and then you have a very good performance for horizontal. I mean, I would just suggest, so you could have tamed a little bit the discussion that the slide 9 has brought by perhaps indicating, breaking down this entire data set and accuracy into, let's say, these 3 figures. They are given accuracy for the for still very significant subsets of, and that would indicate, where this majority of the error in that comes in within this general figure for the entire data set, right? Just a suggestion, I guess.
Yeah, that were my comments on your mentioning the difference between multilateral and vertical regular wells. So my point was that multilateral wells are represented in a database like any other treatment. So, for example, for the horizontal wells, we have a parameter with number of the stages, and for every other parameter, it's regular vertical wells. But for the multilateral wells, it's different because it's very hard to all the formation parameters from different layers into one row. So we need to somehow, maybe we need to average. We need to have some, I don't know, any other tricky methods to aggregate, to sum up, to mean or take median from several layers the well is operating.
You see. So I see. Basically, if I understood correctly, the multi-layer ones, they have effectively a very large weighting in the overall error count, right?
Yeah, yeah.
Because of that. Okay. And another question on I guess it's slide 29. So still sort of dwelling on the predictions, the model prediction. I was wondering, so you show here so these wells in the study, you show the predicted production in red and how you would optimize, what you would suggest to optimize the production using your model, right? So it both are the model output, correct?
Yes, it's a production for the real design and the optimal one.
Yes, as suggested by your ML model.
Mm-hmm.
I would recommend, I mean, in this graph, it would be very, to me at least, very beneficial to have a third bar, which is the actual production. So we could basically, relate what the model suggests, predicts, and what the optimized model suggests versus, versus the real one.
Yeah,
Again,
I have missed it.
Yeah, it's just a comment, but I think it would be even more informative plot on many
For
levels.
Sure.
And I guess, well, I'm not sure if I'm occupying too much of your time, guys. Are we having a single round of questions, or there are So should I ask all my questions now?
Yes.
Yes. Okay. Great. Okay. So maybe one more question. So that was actually the item number 3 in my written comments to you, Viktor. And I don't think there is any record in this recorded log of changes that you provided. There was no answer, or I didn't see it to that question. So perhaps I'll repeat it or rephrase it and see what you say. So, well, it relates to the basically ML forward modeling as your thesis is about, versus the physics-based forward modeling, right? So you know, of course, I mean, you've done a very, seems like, you know, although I'm looking outside the field, you've done an exhaustive work. You've done plenty in this thesis, right? But if I were, you know, ask for my wish, or would sound my wish to you, is basically could one get some sense of how the two methods of forward modeling, you know, are pitted again? How do they compare for some existing wells in your study, for instance? So could you take the same inputs that you had for a given performance of a given well and all the parameters aggregated for that well, right, that you had? Can you use this as an inputs for a physics-based model? For instance, the one coming from Professor Asiptsov group, you know, the hydraulic fracture simulator, or some others. And how would that physics-based model with the same inputs would perform, for instance? So very basic sort of interest question. Or I don't know, have you had any attempts, or within the group, maybe not you personally, but within the group that you have, to look at that?
Yeah, so the answer is I don't know about the what possible outcome if you will, for example, edit some simulator data into the input and train our model on data also. But as for the attempts, we had actual petroleum engineers that were testing our application. They said that so the test was to optimize the production on the newly developing oil field, which were similar to the one we were using. So they used this approach with similar wells within the previous oil field, and they go through all the optimization steps, and they received some optimal design parameters for maximizing the production. And then they tried to do the same, but using the commercial simulator. So the results, if we are doing the same optimization within the same limits, was clear and quite logic. That was their feedback. So
sorry, could you repeat your last sentence, because again there was some Zoom issue.
They tried to do the same optimization within the same limits, design optimization limits, and they received similar result as our optimal values. They received the similar, so it was quite good. That was their feedback.
Yeah. Okay. Is that in an open source sort of a study, or it's
no? It was under
confidential.
Yes, it was NDA, so
it
wasn't published.
Yeah.
Yes.
Okay. All right. Well, thanks. I'm satisfied with my curiosity. Thanks.
Thank you.
Thank you very much, for question, comment, and discussion. And now, Dr. Dontsov, do you have any question?
All right. Yes, sure, I do. So, do you hear me well, guys?
Yes.
Okay, sounds good. So, I'll second Dmitry that, so my background is more on a physics-based modeling and hydraulic fracturing, and so my questions are sort of related. So actually, my very first question was already, asked by Dmitry. It's about comparison with physics-based model, but I want to, expand this, a little bit further. And so my first question here, kind of like the follow-up, is, I mean, so if you did the comparison with physics-based model, right, and you found that optimization results are similar, right, so that, in a way that, the physics that is built in physics-based model is consistent, right, with what we see in the field, right? So which is good. So, but can you train your model from numerical simulations, right? So, for instance, in places where you don't have data, or you don't have enough data, or you change something which is again not reflected in the data, so can you use numerical simulators to train your model? Because I mean, your model is still going to be in orders of magnitude faster than full-scale three-dimensional model, physics-based model.
Thank you. So as for the training on the synthetic data set, it could be our next to enhance the accuracy of our model. We didn't do it through this in this study, but we were comparing the same activities. We were reviewing same activities done by other researchers in the papers. This research say that so-called meta models data-driven, based on the numerical simulators, are very good to generalize all the trends, and they have an accuracy of 10%, and they're very successful in optimizing, or not optimizing, but predicting the output of the numerical simulators given the large data set. But we didn't find any study that incorporates a numerical simulation output into the existing field database. So it would be very interesting to know what would happen. So it would be a logical next step in future work. Yeah.
Okay, thank you. So my next question is sort of more of just more philosophical, if you wish, or maybe just answer the way you think it is. Just ideally, see, so we understand certain physics fairly well, right? And so that's what we incorporate in physics-based model. Like things like Darcy's law, right? I mean, you have more permeability, you're gonna have more production, right? You might have more pore pressure, you're gonna have more production, things like this, right? Or you pump more, you're gonna have bigger fractures. And these are, the things which are, incorporated into physics-based model, right? But here you kind of try to sort of neglect this knowledge, if you wish, right? So, and so do everything from database, right? So, which is fine, which is, great. But is it possible to combine and somehow implement this simple, relatively simple physics? I'm not talking about implementing the full, physics-based model, but in a very simple physics, is it possible to add some very simple physics to the model to, the one that we know and we are very confident, right? So that the machine learning model would actually focus on things that we don't understand, right? Because there's certain things we don't fully understand in hydraulic fracturing, right? So, or sometimes maybe we miss some data, right? So can you, I mean, what's your thinking on combining, trying to implement, simple physics that we know into this ML approach?
Mm-hmm. So as for the simple, relatively simple physics, we can actually incorporate in the form of additional features. So we can somehow find some features that can be used for the model to get the output for the production target data and perform some easy, I don't know, mathematical calculations to calculate to get the additional features that we use to train our model. So it would be, actually it would be, yes, and another one good future work step.
Okay, sounds good. Thank you. I mean, I'm glad to hear that it is possible because again, you know, we need to incorporate things that we know into the model, right? So that make sure that you know, we learn on top of this, on top of what we know already. Anyway, so my next question is the following, right? So you have here in a vertical well, horizontal wells, but I know at least for sure the way that, you know, things are going, you know, in the US in terms of the development is that, you know, people try to do bigger pads, right? So they do multiple horizontal wells, and well-to-well interaction and stacking is really a big issue. So for instance, you know, I mean, I was at a workshop, you know, months ago or something, and so there was people from Chevron and Exxon, they were just you know, just saying how big are the pads they're developing right now. So one of them was like 60 wells, like 60, so 60 horizontal wells. And so that now they, you know, the question that they're trying to answer is how to simulate all this. Do you want to, you know, what's the well spacing, vertical, horizontal, and you know, and this is on top of how you pump, what's your how many clusters you have, and you know, things like this. And you know, it's a question how you simulate inside out, outside in, left to right, and so on. And so what would you need for, because I mean, essentially I'm trying to say that this is where, you know, things are going. I mean, eventually that's where things will probably go, right? Because that's economically more viable to stimulate large volumes, you know, at the same time. And so what would you need to do in your model, right, to account for this, essentially to try to solve this problem, right? I mean, you know, one obvious answer is going to be we need a lot of data, but you know, the bigger the pads are, the less data you're going to have, right? So can you somehow utilize the results of for single well, maybe 2 or 3 wells, and then somehow apply it to multiple wells, right? So I mean, multiple, like 50 wells, for instance. And again, for a physics-based model, you know, doing simulations for 50 wells is really hard, right? So it's really a big challenge. So again, so they cannot, you know, fully simulate, you know, the whole thing. So, but this model is very fast on the other hand. So, but can it handle it? And so, what would you need to do in order to try to solve this problem? But you can start on with 50 wells. So say, I mean, so, you know, what if you have 5 wells, right, or 3 wells? And they're all interacting, right? So maybe you have fractures, you know, grow from one well to another, so they cross, and so there is a fluid exchange and so on.
So for the, I don't know, for the several tens maybe of wells, it would be it's most likely wouldn't be possible to construct a valid and rigid machine learning model, especially in complicated conditions such as unconventional reservoirs. But here we can, we may attempt to do the we discussed previously about incorporating the numerical simulators data. So if it's very hard to do the simulation for 50 wells, and we need to somehow know the interaction between them, maybe it would be possible to train a model on the synthetic input on the fewer wells, and then test it on the more wells, see what would happen, what accuracy we can get, and what knowledge the model could catch. So it would be, I think, most logical step is to do a synthetic input, because it's really very hard to deal even with the big database. So it would be practically impossible to do it on the tens of us.
Yeah,
Straightforward approach.
Yeah, I mean, this is, I mean, again, this is very challenging problem. I mean, I just want to, you know, outline this just so that you know where, you know, things are going, or likely are going. So that's, because we always need to think ahead what to, you know, in terms of our capabilities. anyway, so the last question, and it's not a question, it's more like a suggestion for this tool that you showed. I mean, I think it's very cool. I mean, yeah, all these ones, so that engineers in the field can do optimization very quickly, because a lot of people do these things, similar things with physics-based simulators. It's just much slower, but that they really plot the same things, as you shown here, on the bottom left. So this is very, very nice. So, and just for the suggestion for this tool, I mean, so one thing would be very, very nice is to just keep populating database, right? And so the more data points you have, the more the more you extend the validity region of your model, right? So it would be nice for users to be able to add their own data. It's part of validation procedure, right? So that they optimize it, right? And so they have certain prediction from the model, then they put the real data. But then this data point, if it gets stored automatically in database, and now over several years from many people, now you can double, triple your database. Then it's gonna be really increase your predictability of the model, right? But I'm trying to say that sort of trying to collect data automatically from users, right? And so and give them feedback based on the new data, right away. This would be, very, very nice addition for this kind of user interface thing for the model.
Yeah, actually, it was an MVP of our application, and after that, we constructed an API to deal with such data. So another company was working on automatically gathering data from the different sources in the company's infrastructure within the perimeter of the company. It's in progress right now.
Yep. Sounds good. Thank you. So I don't have any questions and comments. So I'm fairly satisfied with all your changes and replies to my review. So thank you.
Thank you.
Thank you, Dr. Dontsov. Thank you. Please, some question from the colleagues present here or in Zoom. Any question, colleagues? No? Maybe our colleagues online? No? Thank you. In this case, some question for me. You named 6 design parameters which optimization is performed. My question is, why did you choose exactly these parameters? Because according to the feature importance, these parameters are not very important.
So if we come back to the feature importance, we can see that not all of the design parameters are presented here on the top 15 of the top 15 parameters, but these parameters are the most important in the throughout all other parameters. So we have here well construction parameters, formation parameters, and for the design parameters, all of them are in the top 15, but they are in the following little bit less important parameters. But these actual parameters were discussed with petroleum engineers, and they said that they are most interested in exactly these 6 parameters. So that's what I answered.
Thank you, I'm satisfied. In this case, let me give the floor to the scientific advisor, Professor Andrei Sivtsov. Please, Andrei.
Professor Fortin.
Just one question. Oh, please. No, it's figure 9. I come from aerospace where we control the physics and we can observe it a lot more. When I see accuracy of 97%, we can't even get to that level in aerospace when we observe. And you have here a much more complex phenomena with many more variables and unknowns on the ground. So for me, 97% is not credible. And I would like to think it's suspicious. I don't believe it's possible. What do you think?
Well, I cannot comment on the fraud any other, I don't know, suspicious activities the artists were performed. But we should see the data. Maybe it would eventually will come on course, but we don't know.
So before I come to actually to the topic of my speech, just a quick comment to follow up on this one. When we started this work, we have papers also coming from Russia, where the model was trained on 100 wells. 100 wells, not 1,000. And there was a bit of overfitting. The figures were very high. So, but the reason for those high scores was just the overfitting, too small data. This is why we took the ambition to large database. We don't know. Yeah. So this is what Viktor is saying. Right. So yeah, from my side, supervisor, actually there was a team of us working with Viktor. There was myself, also my colleague Evgeny Burnaev, who contributed a lot on my side, and our colleagues, I mean Sergei Borodin and others, and Albert Weinstein, who is online here. He was managing the project with field. So we all are very much satisfied with the work done by Viktor. I should say that this PhD project was the chance for Viktor to learn in many ways, and we arranged it in such a form that this was a joint industry project with the client, with Gazpromneft company. So it was our push project, not their pull project, right? So we proposed the topic. We had an ambition to work on large database. And Viktor naturally came to us to join the team, and he took a specific role within the project team. This is a multidisciplinary team, and it's a huge work by himself and his colleagues. He has his personal contribution. He had his leadership in meetings with, I should say. So not only technical skills were acquired, but also a lot on the soft skills side in the idea, in defending the idea in front of the client, in managing very tight discussions with the people who want the result now. And we had that a lot, especially in the stage of designing the field test. And it was not just with our good partners in St. where there is a scientific and research center of Gazpromneft, but it is their field organization, which, well, they have some appreciation of, but they are doing business in very tight conditions. And I said they need the results now. And Viktor was very strong in front of them. Now, coming back a bit on the scientific side, we had an aim of publishing the papers, and the fact that we did publish, and Viktor, one of the key contributors, is the leader there. So it is, to me, the manifestation of the high level of science behind this work. So overall, I mean, we're happy and we're pleased to see this work is complete. So from the team of scientific supervisors, full support of this work. I'm done. Thank you.
Thank you. Professor Evgeny Burnaev is absent, so we should go to the closest deliberation now. Thank you. And we go to the Zoom breakout room.
So yes, dear colleagues, let me take the floor for a while. We kindly ask all the audience to leave the room. Yes, including Professor Asipetsov. Dear audience online, you're most welcome to stay online with us. We will open a breakout room for the jury members only, but once the jury is ready with their decision, we will be back for the announcement of the results, so please stay in line at this moment.
Dear colleagues, the jury made an unanimous decision that his dissertation is accepted as is, that the dissertation satisfies all the requirements of the Skoltech to the dissertation, PhD dissertation, and the author deserves an academic degree, Skoltech Doctor of Philosophy. Congratulations you, Viktor, and congratulations your scientific advisor too. Thank you.
Yes, thank you so much, everyone. I really want to thank all of my colleagues, friends. Special thanks to the supervisor, to my co-supervisor, to my colleagues, to the jury. Many thanks to my wife, my parents, my friends. So thank you all. It was a pleasure. It was a hard but satisfying journey. Thank you.